Well, hi everyone, and welcome to the last SPAAM seminar of 2024. It's very upsetting, but we have two amazing speakers talking to us today. So first of all, we'll hear from Matt Bowditch talking about adversarial purification using diffusion models.
Okay, hi everyone. So I'm going to be talking to you about adversarial purification using diffusion models. So I'll explain what that all means, first with some background stuff. So the first thing we need to understand are image classification models. So these are designed to classify input images into a set number of classes. And these days, typically deep neural networks are used. And there's many sort of real-world applications for these things, such as self-driving cars. So you can imagine a self-driving car. It's going to need to be able to recognize different road signs and things like pedestrians crossing the road. These models are also used in medical diagnosis and things like facial recognition systems. So I'm sure a lot of you have these on your phones these days. And the reason I brought up these applications is that, in particular, they have large consequences if models misclassify their inputs. And so we want to make sure that they are secure and robust to attempts to fool them. And I'll give an example now of how we might fool one of these image classification models. So yeah, deep neural networks in general are actually quite easy to fool, and adversarial examples are quite easy to find. So the goal of our attacker throughout this talk is to find an image which is misclassified by the system, but also whilst also maintaining high visual similarity to the original image. So to give an actual example, here we have a physical adversarial perturbation. So on the left, we have a stop sign with just some regular graffiti on it. And on the right, we have a stop sign which has an adversarial perturbation applied to it physically. And these are the white boxes and the black boxes. And these have been crafted in a way to fool an image classifier into thinking this stop sign is a speed limit sign. And you can see it still looks quite similar to a stop sign. And if you saw it while you were walking around, you might not think twice about it. And so yeah, this is sort of one of those examples which would have a large consequence if it happened in a real life scenario. Okay, so I'm going to briefly talk about some of the maths behind finding these adversarial examples. So our attacker starts off with some image, X, and some classification model C. And our attacker wants to find some X prime, which is going to be the adversarial image, which satisfies the following two things. So the left-hand side, we typically use some measure of image similarity, and this makes sure that the adversarial image is similar to the original. So we want this norm to be less than or equal to some tolerance, some epsilon. And we also want the adversarial example to be misclassified. And so our attacker's chosen some target class T. So if we think about the stop sign, they might choose the target class to be a speed limit sign. And then we want our classifier to classify this adversarial example as this T. So like, how do we find this in practice though? That's the goal. To actually find such an X prime, we typically define some sort of optimization problem. And so this is what it might look like. So on the left, we again have this measure of image similarity. So we want to try and minimize this. And then so we want to minimize the difference between the original and the adversarial example. And then on the right, we typically define some loss function. So this gives us some sort of measure of how close the adversarial example is to the target class in the output of the neural network. And like this loss function typically looks something similar to the kind of loss function we'd use to train our neural network. And because of that, and because of the way neural networks are designed, we can actually calculate the gradients all the way through the neural network. And so this optimization problem is actually quite easy to solve using some sort of gradient-based method. And so yeah, we can quite easily find a perturbation that we apply to our input image that causes the desired output to move closer to the target class. And we can sort of calculate gradients the whole way through. And so it's quite easy to find which direction the perturbation needs to go to cause this effect. Okay, so yeah, this is attacking or finding adversarial examples. I'm interested at the moment in finding defenses against such examples. So a couple methods that have been used involve, one of them is adversarial retraining. So what we can do is we can include adversarial examples into the training data when we train our neural network. And we hope then that the neural network kind of learns how to deal with these. And then when it encounters one, when it's being used in the real world, it should hopefully still classify it correctly. The next one would be trying to detect the adversarial examples. So we could train a separate binary classifier that sort of says, given some input, it says adversarial or not adversarial. And we can apply this before we try and classify the input, so we know if it's adversarial or not. And then the third one, which is the topic of this talk, is purification. So what we do here is we attempt to transform the adversarial input to clean data before feeding it into our neural network, so that the prediction of the network is not affected. And this has the benefit of we can still classify our input because we essentially recovered the original image given the adversarial image. So yeah, I mentioned at the start, we're trying to use diffusion models to do this purification process. So quickly, I will describe how diffusion models work. So we start off with some large data set. So throughout this, I'm going to be considering images. So we can imagine some large data set of images. And then we can train a diffusion model using this large data set in order to generate new samples from the distribution that data set is kind of approximating. And the way diffusion models work is we have a forward pass. So we start off with a clean image of a dog on the left there, and then we add Gaussian noise until at the end we sort of have something that resembles just pure noise. And then the interesting part of the diffusion model is the reverse path. So how do we go from noise back to a clean image? And the way we do this is we take lots of steps, and each step we have a neural network that can take in a noisy image and kind of predict the clean image. And with what we do is we use this prediction to remove a little bit of noise at each step, and eventually we end up with a clean image. So what a diffusion model then is kind of learning to do is find a path from sort of pure Gaussian noise on one side to distribution of images on the other. It's kind of learning to find a path between these two distributions. Okay, cool. So that's all the background anyway. So now we can talk about how can we use diffusion models to purify adversarial examples. So yeah, this has been done in this paper, DiffPure. So what they do is they add a diffusion model prior to an image classifier in an attempt to remove adversarial perturbations from images before classifying. So the way this works, so you see here we have an image of a panda. On the left, an attacker's added a perturbation to the pixels of the panda to make an image classifier think it's actually a gibbon and not a panda. DiffPure then adds a bit of noise to the image until we get to that center image there, so we kind of have a slightly noisy panda, and then takes the image through the reverse diffusion process and to get back to a clean image, and then classifies it. And you can see in this example that the image classifier now gets the image correct and correctly identifies it as a panda. And it's interesting that this works because there's nothing special about this diffusion model. It's kind of just an off-the-shelf diffusion model. It hasn't been trained on adversarial examples or anything like that. But I think intuitively, it kind of makes sense why this works, because diffusion models, like I said before, are trying to sort of find a path from noise to the clean distribution of images. That's what they're good at doing. And so when the diffusion model sees an adversarial example, which is kind of a bit away from the clean distribution of images, it's also quite good at sort of moving it back towards the clean distribution of images and removing the adversarial perturbation from the image. So yeah, that's DiffPure. So my research at the moment is looking to improve on DiffPure. Since DiffPure's already been attacked, so someone's already found an attack that works quite well against DiffPure. It's kind of the nature of this field as you get in these cycles, attack, defense, attack, defense. So yeah, now we're trying to look at defense again. And we're trying to improve this method by sort of introducing some additional guidance to the reverse diffusion process. So to understand that, we're going to need to understand the reverse diffusion process a bit more. So I sort of said at every step that a little bit of noise is removed from the image. And to predict this noise, we use some large neural network. And it typically has this kind of architecture. So we feed our noisy image in on the left, and then you can see that it kind of goes from a high dimensional space on the left and moves it to a lower dimensional space in the center. And this lower dimensional space we call the bottleneck. And then the image is moved from this low dimensional space back up to the full image space. And so we can kind of think of the neural network as encoding the image to a low dimensional space and then decoding it back up to the original space. And what's interesting about the bottleneck layer is what it actually kind of learns about images. So these units actually kind of learn semantic things. And so you can imagine if we had two pictures of dogs and we put them through this unit, it kind of recognizes what a dog is. And in this bottleneck layer in the middle, the vectors might look quite similar because the units kind of recognize that these are images of dogs. So this is kind of what we see happening with these units. And people have noticed this, and they found that they can move the vector in the bottleneck to change semantics of images. So as an example, if we found what the happy vector looks like in this bottleneck, we could sort of add a little bit of that vector in the bottleneck while we're going through the reverse diffusion process, and maybe kind of push our image towards being happier. So this has been done. So you've got a dog here, the second from the bottom. That's the original image. And then they've kind of, I won't be able to go through all the details of how they find this vector, but they kind of have found some sort of happiness vector in the bottleneck of the unit. And then they add this during the reverse diffusion process, and the dog smiles at the end. And they get really good results with this. Another quite interesting thing is that if you subtract, if you subtract the happy vector, the dogs kind of get sad. Which is like, it's interesting that the unit kind of knows it has some kind of linearity within it. It's kind of like the opposite of happy within the bottleneck of the unit is sad. It's kind of somehow got that linearity, which isn't necessarily immediately obvious. Cool. So that's that. So yeah, I'm basically trying to combine these two ideas. So Diffpure, which is adding a diffusion model to image classification, and then this understanding of what the bottleneck is doing in the unit. So if we imagine, for example, that picture of a panda, there's many semantic things we could change about that image whilst still classifying it as a panda. So if we kind of use our diffusion model to change semantics of the image whilst still maintaining the class, we can maybe have a more effective way of removing adversarial perturbations, is the general idea. And yes, that's broadly what I'm looking at the moment, is trying to find directions that improve Diffpure. So yeah, we're trying to find vectors that help to constrain images to classes we're looking to classify, and hopefully that would help guide adversarial images even more so towards clean images. Yeah, so that's a very quick outline of the kind of stuff I'm doing at the moment. Thank you for listening.